Yeah, and maybe we should just like. If I
ever get, I'll take a reach. That's fine. If I ever get the trust of in the.
Okay, cool. So, hello everyone. Yeah, great. I got everyone's attention. Thank you for coming to today's talk. Today we have Strubell from CMU talking about environmentally sustainable AI challenges and solutions. Emma is a Raj Reddy Assistant Professor, now just promoted to Associate, effective in summer. So not the official title yet, but they got a promotion. They're Assistant Professor in LTI at CMU. Previously, they held research scientist roles at Google, Bayer, and AIU after earning their doctoral degree in 2019 from UMass Amherst. So we're teammates. Strubell's research lies at the intersection of NLP and machine learning, with a focus on providing pragmatic solutions to practitioners who wish to gain insights from natural language text via computation and data efficient AI. Their work has been recognized with the Madrona AI Impact Award, Best Paper Awards at ACL and EMNLP, and in 2024 they were named one of the most powerful people in AI by the. So I'm gonna tell a little bit of a fun fact about when they made the slides about their best paper at ACL. They made this awesome transformer animated slides. So if you ever take mine, just learn that on Michael's NLP Plus, we are still both using their transformer animated slides. As am I. Yeah, it's a really awesome animation. And then the next year, when they win the best paper again, their topic is environmental. I think one of the first papers looking at the environmental impact of all the environment. Same as today's topic, more on this environmental system. So let's welcome that. Yeah, thank you so much for the kind introduction. And I'm excited to finally be here after being in Pittsburgh for so long. Actually being able to schedule and give this talk. So today I want to talk a little bit about climate change and AI and the relationship between them. Okay. And so I'm hoping that I don't need to convince anyone in this room that climate change is like an urgent, complex, and unsolved problem. And trying to do our best to sort of tackle this problem and adapt to or mitigate the impacts of climate change is going to require collaboration across many disciplines, across many geopolitical entities, just like a really, really complex and difficult problem to solve. I have a fun picture. It's impacting me and maybe all of us. This is like my street in Pittsburgh that has collapsed due to a sinkhole. And these are the types of things that are happening globally due to arising from climate change. So for example, in Appalachia, Pittsburgh and the greater Appalachia area, one of the ways that we see climate change impacting us is through increased extreme weather events and changes in weather. So having a lot more rain tends to cause our geology to sort of landslide and sinkhole. We see a lot of Pittsburgh is now sort of known for their sinkholes. So, as an AI NLP researcher, of course, it's something I care a lot about, and I'm thinking about how can my work, hopefully sort of contribute to solutions in this space. And I think AI actually has great potential to help mitigate climate change. So one example of many is in decarbonizing electricity. So in the United States, about 25% of greenhouse gas emissions are arising due to electricity. And basically our electricity demand is only going to increase as we try to replace fossil fuels with low carbon energy, right? So think switching from combustion to electric vehicles, switching from burning oil or natural gas to your home to okay, and so if you haven't really thought about electricity before, basically electricity use involves sort of three, it can generally be divided into three sort of stages. There's generation, which is creating electricity, transmission, which is moving electricity from the places where we generate it to the places that we need it sort of at a larger scale. And there's distribution, which is sort of getting that larger scale electricity to actual houses and industrial places. So across all of these areas, I can give just like a couple examples of like challenges and like perhaps AI capabilities that can help to address those challenges. So for example, to help in renewable energy generation, an interesting problem that I've actually worked on with collaborators in material science, sort of figuring out how we can identify, inexpensive, sustainable photovoltaics. So to sort of make solar energy sort of better for the environment, more affordable, and able to scale better. And perhaps that's what we're trying to do. There's other ways to do this as well. Let's figure out how like LLMs as research assistants can help accelerate that process. So another example in energy transmission is it's actually a very challenging problem to manage an electrical grid. It's like a huge complex system with also like really large physical, sort of slow-moving and fast-moving parts. And so aligning changes in supply and demand is like a really difficult optimization problem. And machine learning-based forecasting, for example, is something that can help with that. And then in terms of distribution, one challenge is how long do I want to go to this? Basically, when we, so this is another thing that was happening in Pittsburgh before they put in a new substation, actually near CMU, is in the summer at like 5 p.m. And I was just pretty regularly at my house losing power. That's because everyone was getting home from work and turning on their ACs in the heat wave. And the way that this sort of like fluctuating supply and demand thing is handled is like when we run out of, for example, renewable or maybe better sort of versions of energy, sometimes we need to go higher. And so they turn on the sort of backup fossil fuel-based sources. And that can even look like going from natural gas to like coal, which is sort of like a dirtier source. But they have to turn on these sort of like more integrated, less efficient sources. An alternative would be, as everyone starts to adopt like EVs or even just like solar with like batteries powering their home, we'd really like to move towards a more distributed model where we can instead draw upon these distributed battery sources as backup power. But this introduces, an interesting challenge of so how do we control this like battery charging and discharging? Ideally, using renewables aligned with like increased wind or solar energy availability. So there's some really interesting sort of like RL control problems there. Okay, so this sounds great. Like AI, the solution to climate change. And that is like also the sort of narrative I think that you'll hear from a lot of sources, especially large companies who are like doing a lot of AI. But at the same time, we're seeing these large companies who are doing a lot of AI sort of like in the news for their contributions to greenhouse gas emissions. So these are some reporting from last year based on Google's environmental sustainability report, which is sort of like companies release reports every year. This, for example, includes greenhouse gas emissions and other things. So for Google last year, despite committing to reduce their carbon emissions in half by 2030, and they did that commitment in 2019. As of 2024, they had actually increased their emissions by about 1/2. And this is a trend that we're seeing, this is not unique to Google, this is unique to sort of like all the big players in terms of technology firms. Baidu this year also reported a 20% increase in greenhouse gas emissions, and they're explicitly pointing to LLMs basically as the reason for that. Microsoft this year is reports a 23% increase over 2020 due to AI and cloud expansion. And then this also goes beyond just like technology firms to sort of like government initiatives and things. So the EU has a CHIPS Act, just like the US CHIPS Act, which is sort of trying to move basically chip manufacturing more locally. But if they actually achieve the production goals that they want to achieve per the CHIPS Act, it's estimated that this would like increase the emissions of that sector in the EU by like potentially 8 times, which would make it more emissions than industries that are considered pretty high emissions, like steel.
So this is unfortunate. So now we need to think about how do we sort of square these challenges. And so like entities that kind of look at this stuff, like how do we meet climate goals, like the IEA, can make predictions, but how much do we need to decrease emissions per sector in order to meet these goals? According to the IEA, for example, they say that we need to reduce greenhouse gas emissions due to data centers and data transmission by at least half by 2030 in order to be on track with IPCC goals. So this is something that I think about a lot. I think like artificial intelligence has great potential for both positive and negative impact on the climate and on our environment. And so how do we think about that? How do we achieve that? I think it requires some sort of like careful understanding and thinking in order to ideally sort of shape a future where we're getting the benefits, and those benefits are sort of outweighing the costs. Okay, so for the rest of the talk, here's what I'll talk about. I'm going to start by talking a bit about like what we do know about the current environmental footprint of AI. I'll talk about what we don't know. So what are some key knowledge gaps that are sort of holding us back from doing more? And then talk a little bit about like sort of what next, maybe what you and I and like what we can do, how I think about that. Okay, so first I'll talk in a little bit more detail about how AI actually does impact the environment. So probably what many people are used to thinking about is what we call the operational impacts. And that is basically the impacts that arise due to like the development and use of AI models. And I'll give some examples in a second of all of these. Like energy use, for example, causes greenhouse gas emissions. So AI also can have embodied impacts, and those are the environmental impacts that arise from like hardware manufacturing, transporting that hardware, building data centers, like cement production is like a huge greenhouse gas emitter, like globally, I think 30% greenhouse gas emissions. And then disposal, like end of life, we have to do something with that hardware or to not be toxic to the environment. And then really importantly, the actual applications and like what we develop AI models to do and how we deploy them in terms of tasks also has huge potential sort of downstream implications for the positive or negative impacts of AI in the environment. So, like for example, I have two pictures here. Solar cells. One is of this oil derrick. And so, similar AI models could be used to accelerate oil and gas exploration, allowing us to continue burning more fossil fuels, or they could be used again to sort of like help develop the next generation of renewable energy infrastructure infrastructure. And I guess maybe I'll make this point later as well. But something that I want to highlight here is that I think actually, in terms of the scale of potential positive or negative impacts, this downstream applications thing is actually going to be much bigger than like sort of what arises like strictly negative environmental impacts arising from energy use or like manufacturing hardware. Yeah, so some specific examples. So like greenhouse gas emissions arise from like fossil fuel-based data center energy. But greenhouse gas emissions are not the only way that AI impacts the environment. So we also have water withdrawal and consumption, and that arises also from many different stages. But in particular, evaporative cooling is like one of the most effective ways, or most prominent ways, certainly, to cool a data center. Its hardware produces a lot of heat, wastes heat energy, it needs to be cooled more efficiently. And most data centers use evaporative cooling, which uses water. It's also often potable water. There's a lot of like really interesting things that I won't talk about today. Potable water takes energy. So deforestation is another negative environmental impact that arises from AI, and that can happen primarily from the mineral extraction that is required to build the hardware. And I'll talk about this more later. But there's also sort of like downstream, like economic rebound effects. So like the way to think about that is so more in this downstream space, like thinking about how new technologies that arise from AI or AI itself can actually change the way that we behave as individuals in the world, and how society works, and how business works. And that can actually lead to sort of different outcomes in terms of environmental impacts. Okay, so now to hone in a little bit more on language models. So why are LLMs so resource intensive? Like, why is this a problem now and it wasn't a problem before? This is because the state of the art. Okay, how many people in here actually are like NLP LLM people? Is everyone LLM program? Okay, okay, so I'm not, okay. So I'll talk about this. I'm just used to, yeah, my department is like an NLP department. So I'm like, okay, CS is like actual, yeah. More diversity here, it's good. But you may still know this anyway, LLMs are sort of like on now. But I mean, basically the issue here is that the state of the art for advancing AI capabilities is largely just like increased computation and energy. And so traditionally, this has largely been scale and training. So we want to train models on as much data as possible. That's going to lead to best performance. And in order to actually learn from all that data, we need to make the model bigger in terms of the number of parameters. And so both of these things scale the number of computations we need to do, which then just requires more energy and more hardware production. And so these are just sort of two examples from various papers demonstrating like the impact of model scale, model size on performance. So not worrying too much about the details of these plots, but like the general idea being that accuracy is what we're looking at, like task capability essentially is what we're looking at on the y-axis. On the x-axis, we're looking at increasing like computation or energy use. And you see that like as you increase computation, it's largely it's like across a bunch of different tasks. Different model scales so more recently, it's become less effective, kind of scaled training to the extent that is useful. So now instead we've moved to scaling inference. So given one of these big models, it's like how else can we sort of add computation in order to get more performance? And so when you see like thinking models and reasoning models, this is essentially what they're doing. So instead of making the model itself larger, they're adding computation in the form of more input tokens. So they're sort of changing, making the input size bigger and making the output size bigger. So generating more tokens to sort of do this reasoning. And so this is more of like a scaling and inference testnet. Yeah, so again, these are just like a couple like demonstrative figures. So on the left here, you have basically just looking at like number of tokens on the x-axis and like actual energy use on the y-axis of a large language model. And you see it's so the y-axis is actually logarithmic here. So it's x actually. So this is very wrong, actually. Oh, well, yeah, okay, both axes are exponential. That's fine. So basically just linear-ish relationship between energy use and input-output token lengths. And then this is a figure from the DeepSeek R10 paper. It's like demonstrating how one of their key contributions was that during training, they were able to get the model to produce like longer and longer output lengths or response lengths, which enabled them to achieve better performance, but also like more computation in terms of that aspect. Okay, so what does this actually look like? Sort of like top down at a sector level. I won't spend so much time. But to get a sense of this, and you'll note that some of these numbers are like really old, or I think 2020 is like quite old. But one of the key points I want to make here is that we're really lacking in data right now to even sort of like understand this. But so the last one we told us was about 2020, and at that time, or I guess from 2019 to 2021, AI made up 10 to 15% of Google's total energy consumption, which in 2020 equated to 1.5 to 2 terawatt hours of energy. And you may have seen the news from September a couple years ago that Microsoft signed a deal to reopen the Three Mile nuclear power plant, basically in order to power AI data centers. They purchased, in order to do that, they purchased energy equivalent to about 800,000 homes over the next 20 years. But yeah, basically, yeah. I'll move on a little bit. Okay. And yeah, and so importantly, I think for this audience, you'll probably like find this, but like this energy use, is made up of very different, like a bunch of different sort of use phases or like life cycle phases of a machine learning model. So inference, which is when you're using it at test time. Training is when sort of, I guess, the model is being trained on data. There's also development, which is like figuring out even what the model sort of should be, and what the data mix should be. And importantly, we have like the energy per inference is actually very small. The frequency is extremely high, whereas in development, very few entities actually have the computational resources or financial resources to participate in that. So like, the sort of energy use from that is very high, but it happens very infrequently. If you're interested, I don't know, this is maybe too nerdy thinking about this, but I think this is really cool and interesting. It's also a little bit old. This is like a breakdown at Meta from a few years ago of like where their AI energy use sort of goes in terms of these life cycle phases. And I think this is potentially even more so the case now. Like 60%, 2/3-ish is going to inference, test time, 1/3 going to training. And it's super interestingly, so this bar down here is like the breakdown for one of their recommender models. You think like Instagram ads or like Facebook feed or something like this. And so the black part is like inference, essentially deployment. The striped and orange parts are training. And this yellow part is data. So this is actually the energy that's required to just sort of like, look at your data as you're using their products and like convert that, like filter it, clean it up, like convert it to something that can be used to do this like continuous training of their models. So that's also like a really important sort of factor. Okay. So yeah, okay. So that was sort of like top down, what does this energy use look like? We can also take like a bottom-up approach to sort of like understand what the CO2 emissions look like. And so the next couple of slides are going to be about a paper we published iClear last year. There's a collaboration with folks at AI2, where we did like a really fantastic detailed data and deep dive on the energy, water consumption, environmental impacts of developing the open source models. I'm really excited because we have like a bunch more data now from almost 3, and it's like even more detailed and like all kinds of like post-training stuff. We're gonna do again. Okay. So yeah, so this is how we calculate the like the CO2 equivalent emissions of training a model. And so we can divide it into the operational and embodied emissions. So as I said earlier, the embodied emissions are arising from sort of like the hardware manufacturing and things like this. Operational emissions are due to the energy use to actually do the thing. And we calculate this as the GPU energy multiplied by the power usage effectiveness. So this is like a factor that takes into account basically how much additional energy as like a ratio is required to actually support this computational hardware. So think about like the HVAC and like cooling and stuff in a data center, the lights, stuff like that. So it's at a lower bound, it's like 1.0, and the lowest that like Google's hyperscale data centers achieve is like 1.1. And then we multiply this by the carbon intensity of the energy. So that's sort of like for a given unit of energy, like for like, a kilowatt hour of power, what are the greenhouse gas emissions? So it changes the function of how renewable energy is. Ideally, it would be approximately 0 if you're powering fully renewable energy. Yeah, and in terms of the embodied emissions, we do like an amortized analysis of the expected lifetime of the hardware. So like at AI2, the expected lifetime of hardware is about 4 years. And that's through conversations with like the data center providers that we used. So yeah, so we again sort of multiply the GPU time required for this training, so the amount of time that the hardware was used to do this training, by the manufacturing carbon intensity, which like is like a number that we can estimate, but it's like rough. Not a lot of data there. So what does this look like in practice? So here for llama models and some Homo models are of different sort of relatively small scale. We have like the energy in megawatt hours was used to train them. And then the equivalents, there's like a lot more numbers in the paper, of course, if you're interested. The equivalents in terms of like average US home years of CO2 emissions. And you can see like the llama 3 sort of family of models were pretty energy intensive, about 83 years of the US home emissions, and then so similarly, very similar, basically like equation, but with respect to water use, or multiplying energy by the water usage effectiveness of the operational energy. Energy also uses water. Nuclear power, for example, is like a fun example because it's like basically renewable. It's not producing like greenhouse gas emissions, there's sort of like waste issues, nuclear waste disposal issues. But it does use a lot of water because it similarly requires like a battery. And then multiplied by the embodied consumption. There's also a lot of water use, water contamination, and filtering that goes into hardware manufacturing and production. Which we can also kind of like very vaguely estimate based on the available literature. And this is sort of how that pans out. Notably, the llama, like Meta does not report water use estimates for the llama models. It's possible that Mistral actually did. I should put that number in here. Mistral might be doing that potentially, like per query or something. But for the Olmo models, sort of this is what we calculated here. I'm plotting it, or like reporting it in terms of average US person equivalent years. And so like the Olmo 213B model use like 7 years of the average US person's water, for example. Okay. So that's kind of like the state of things, I would say. So this llama 3 number, it's like pretty high. So llama 4 has happened, and they also sort of reported their estimate of CO2 equivalent emissions for llama 4. It's like an order of magnitude smaller. That's amazing. Why is that happening? You know, they probably were able to like, sort of reuse like various computation that went into llama 3. Also just like efficiency improvements that happen over time. There's like hardware efficiency improvements, as well as sort of methodological software efficiency improvements, optimization stuff. So yeah, so then the question you might ask is like, okay, we're making clear efficiency gains, and we've made clear efficiency gains in the past, like, and fantastically, it's like well aligned with like profit incentives, right? Like the AI companies developing these models like want to make everything more efficient and cost effective because then they can charge less or actually like make a profit, which they don't right now, providing like generative AI services. So is it fine? Like, does any of this matter at all, actually? And now I'm going to talk to you about why it still does. Okay, so and now we're going to talk about like these rebound effects. So this is a figure. So I'm trying to depict the like sort of scope and scale of environmental impacts due to AI. And so as we move from the center of the figure to the outside of the figure, we have this like increasing scope of greenhouse gas emissions impacts, as well as increasing uncertainty. So things become much harder to like calculate, measure, and estimate. And in the very center of this circle here, we have these sort of like compute-related impacts. It includes like the embodied and operational impacts of compute. Goes into the development models. And then, as I mentioned earlier, we have these immediate applications. So you develop this model. What is it being deployed to? Is it, is it assisting in oil and gas exploration? Is it making buildings more efficient, like turning lights off when the ones are room, stuff like that. And so those impacts can be like either positive or negative. And then this outermost area, that's where we have these rebound effects. And that's where we have the potential positive and negative impacts that are arising from like how AI technology potentially actually like changes like the way that society functions. So I think a nice example that I like to think about is like Instagram ads. So you can think about there's like however much computation and energy and greenhouse emissions went into building like the ads model. That's really good. Oh, they're so good. That sort of predicts what to show you when you're scrolling based on your history. And then, but like the thing is, that model potentially leads you to buy more stuff and maybe buy more like wasteful stuff that you're actually not going to use, and that has like a negative impact. And so that's a way in which like a new technology so potentially sort of changes our behavior in a way that has these downstream effects, these system level impacts. And I want to talk specifically about, so because of these rebound effects, I think that data centers are going to consume as much energy as we can give them, driven by AI, regardless of efficiency improvements. And the specific rebound effect that I think is responsible for this is what's known as Jevons paradox. It's coined by economist Stanley Jevons in the like 1800s, it's an industrial revolution with respect to coal production. So the phenomenon that Jevons paradox describes is basically when an increase in efficiency, rather than reducing overall resource use, actually increases the overall resource use because the thing you've made more efficient becomes more accessible, can be deployed and applied in like many other new settings. So more people are actually basically like using it and stuff like this. And so I think this is what we're seeing and are going to see in AI. The Microsoft CEO, Satya Nadella, also agrees with this. He's pretty happy about it in terms of his like business. So from like a year ago, where he says Jevons paradox strikes again as AI gets more efficient and accessible, we'll see its use skyrocket, turning it into a commodity we just can't get enough of. This is like in response to like the concern about DeepSeek, making things too efficient and like US AI companies not doing. And so this is an example of a rebound effect where you have this sort of like paradoxical-ish result in like the sort of like actual use cases that's resulting from some correlated changes in behavior and use pattern systems. You can't ignore the fact that this thing is actually going into the world and that can change what sort of the whole model system is. Okay. So for the sake of time, I can share the slide, you can go back to the recording. I'm not going to go into detail on all these. There's also like a paper about this from FACT last year that we wrote. But there's like many different sort of interesting indirect effects to consider here. And like the reason that we wrote this paper is because I feel like there's been sort of like debate, or like I think there's this debate that I've been involved with about sort of whether like AI and all this energy use, basically is ultimately going to be like sort of good or bad for the environment. And so my position on this is that basically all of the sort of current arguments about this are just like really limited because they tend to not consider these indirect effects. They're very hard to measure and sort of hard to think about, but like both sides sort of saying like AI is good for the environment, AI is bad for the environment, like they're both wrong or like don't know what they're talking about, basically because they're not really incorporating these indirect effects that actually potentially have the highest, the biggest influence on like sort of what that okay, so for the rest of the talk, thinking maybe towards the future, talking about some sort of challenges, interesting things. So I think given this like assumption that I believe to be true, that at least for the foreseeable future, due to Jevons paradox, data centers are going to use as much energy for AI as they can get. I think I'm thinking less about like how do we reduce like the energy use or like environmental impacts of AI necessarily, but how can we think about it as like sort of a budgeting or resource allocation problem? So given like a fixed resource of energy use or whatever, or impacts that we decide we can allocate to AI, so given climate goals, what is like the most effective way to actually allocate and use those resources? What should we prioritize? I think right now the status quo is that people with the most money are sort of making those decisions, or like it's not even as much a conscious decision as it is just sort of like happening to us. But I think we could be a little bit more deliberate. So some of the key challenges and trade-offs in this space, one as I've alluded to earlier, is data and measurement. So we're lacking a lot of the necessary data to sort of like understand this space and sort of what the trade-offs really are. And this is both due to a lack of like sort of methodological standardization, as well as like the entities that have to report this stuff like aren't doing it because we're largely not requiring it, and there's sort of like intellectual property and competition concerns, which I don't. So another key issue that I think is really interesting is, and that I think is critical here, is like this sort of trade-off between specialization and generality. And this is a great example of something that's just sort of like happening, but like not super deliberately. And I think it's a place where like sort of academic people in universities and potentially like play this role. So when you think about efficiency, like how do we, even under this budget constraint problem, right? We still want to reduce, like improve the efficiency of things. We still just like do more. But like the best way to improve efficiency is to specialize. Is to identify, okay, here's actually the specific thing that we really need to do, and let's make a model that just does that really well and really efficiently. Yeah, we have some results to show that, but like, and you can even build hardware that like will specifically do that, and it's going to be like many orders of magnitude more efficient than using, for example, just like an off-the-shelf model, off-the-shelf LLM to do that task. But the specialization, it does require some like upfront investment, like monetarily, time-wise, and it just, which means you have to actually prioritize. You have to decide, okay, well, like, what do we want to specialize on? Like, what is worth sort of investing that effort into to sort of optimize for? And that becomes a little bit and requires more data and cooperation. Yeah, which brings us to the other, of course, challenge. Like, this is not remotely only a technological issue. Like actually achieving any of these things sort of really requires thinking about like what are the incentives for relevant actors to like participate in this type of thinking and the action that's required. And what is the role of like governance and potentially sort of requiring certain cooperation, or like sort of how can we more gently, is it regulatory concerns, or how can we maybe more gently try to align incentives in order to actually implement this prioritization. Okay, probably should take like 5 more minutes. I love the next couple of charts though, so it's just gonna happen. So sorry. So the next couple slides are about measurement, this data question. And I think this is so interesting. So I think this is a great example of how the data is just insufficient for like really important, like basic functions that you can perform. So something that the US and like globally every country is trying to do right now is sort of like forecast in terms of like an energy security perspective. How are we going to power AI? There's an AI arms race. Like, do we have like the energy production ability to like support the data center energy use that's going to be required to like fight this AI battle? And so this is basically a plot. So it's like time and like future estimates on the x-axis, and the y-axis is terawatt hours of data center energy in the US. And the point of this plot is to show you that like the estimates are like wildly varying. And the point that I want to make here is that this is like basically because of a lack of data. We just don't have good models here. It's a lack of like just data, period. But also a lack of like sort of detail and underlying understanding. We basically a little bit more. So yeah, so basically the difference in these estimates for US data center use is about equivalent to like 10% of the total US energy projected use for 2028, which is sort of like an unacceptable margin of error, I would say. And when you look at like global estimates, this becomes like even worse. So let's say this is like sort of the same plot. We're looking at sort of global data center energy use estimates, terawatt hours on the y-axis. I'm like ignoring this one, honestly, because whatever. Clearly that's wrong, hopefully. I mean, I think that's like something like we couldn't, it's like the planet, it's the amount of energy in the sun. It's fine. But even if you just look here, again, it's like multiple petawatt hours of differences across estimates in 2030, which is similar to the energy demand like of all of Europe. So we need more data, we need better models. Oh yeah, briefly, this is actually like a more, I think this is like a nice, sort of trustworthy conservative estimate from a report last year from Morris Berkeley National Lab. Also, it's similar, like projecting energy use. Here, it's dividing that energy use by sort of hardware. So the purple part at the top is sort of like the AI part. And the point I just want to make here is like sort of estimating that AI is actually going to be driving that uncertainty. Purple part is below that. Yeah. So I just demonstrated how. And so this data center energy use is probably some of the best information that we have about AI energy use, actually. And that includes in terms of like mandated reporting. So like in the EU, like all data centers are either already or will sort of have to report their like energy use, their efficiency. In Germany, it's even more strict, where they actually are defining the requirements for new data centers to source a certain amount of energy renewably and have certain like efficiency values. But even here, we sort of don't have enough information to do good estimates and forecasting. And I would argue that, yeah, data center energy use, this really high level, vague, coarse-grained metric, is like totally insufficient. And then I didn't end up talking about this, but I worked with Sasha Lucioni on the AI Energy Scores project, which is sort of trying to do like a energy stars and classification of models in terms of their efficiency to like inform consumer behavior. But these models with their energy scores, I think, are also not sufficient. Like we need a much better understanding of like where this energy use is arising. So is it like training versus development versus use? Importantly, what are the actual AI use cases and applications? This is also a really old table from a paper from at the time Facebook. But basically just pointing out that like across these various different actual services or products, they have very different sort of like energy profiles and needs. How are local communities impacted? So this is such an interesting figure, I think, from an IEA report from a couple of years ago, where without going too long-winded, basically data centers are like an extremely highly concentrated industry compared to other industries. When you think about like, I don't know, coal, like steel and coal, right, as being sort of geographically located in the US, data centers are like way over here in terms of how concentrated they are. What that means is that local communities, in terms of like environmental impacts, the local communities where those data centers are located are seeing like really, really disproportionate impact in terms of their, in terms of like emissions, it's not renewable energy, but also in terms of like their utility rates. These data centers are relying on public utilities, which they do to provide electricity and to provide water. It actually has been demonstrated that has led in the US to increased rates for ratepayers. So I think there's a lot of work needed to understand even how to measure that, what needs to be measured in order to do this sort of responsibly. Yeah, and so we sort of have to rely on entities to report stuff, but they don't. Yeah. Okay, so I want to wrap up. So I think I'm going to basically skip to my last slide. I talked a little bit about specialization versus generality. Yeah, the thing I'm mostly going to talk about there is that I think we can get a lens a little bit into what we are, deliberately or not, what we are as sort of a community and a society, specializing with respect to. So the thing I like to say is that there's no such thing as a general purpose model. Actually, they've just been optimized for like high frequency use cases and like high potential like business income use cases. And we find that, yeah, again and again. But yeah, and so we can look at sort of like what are the benchmarks when we say, oh, this model's, this model release, like the numbers are so high. What are these numbers so high on? And then we can ask the question, like, is that task that we're optimizing for, like, is that the same type of thing that is going to achieve, like our climate goals? Is it the thing that is going to like decarbonize the grid? I think it often is not. And so that's where, yeah, I'm thinking about like, okay, well, maybe, like, I agree with the role that AI could be really helpful in adapting and mitigating climate change. But if you look at the actual amount of sort of like energy and like human expertise and brain power and effort that's being spent on those types of applications versus applications that are aligned with like tech companies' business models of sort of selling ads, I don't see that actually happening. Like if you follow the steps, yeah, that being like that AI is sort of better for the environment. Okay, so wrapping up, role of universities. I recently had to give a talk, and they like wanted me to talk about this, and I was like, perfect. I'm talking to people at university. I can just like throw this in. So hopefully it's helpful. But I think that higher ed can and must play like a critical role in this whole thing. So the easy one I want to talk a lot about is like education and knowledge dissemination. Like, we need to have AI literacy, like even for people outside AI and computing, I think, it needs to include sort of like understanding that this is not a black box, like the cloud is actually a physical thing that with like physical implications in the world and resource consumption, and sort of having that be like a part of AI literacy and the role of universities in terms of like trying to the extent that we can to keep this knowledge open of how these models are built, so we can empower more people to be virtually involved in that process. This is like a shout out to me, I guess, is the thing that I work on. But like universities are also critical. Like I consult with like various governments and things, like the US government, the German government, the EU, like on how they should measure this stuff. Like places are trying to govern this, but they need sort of like impartial expertise from experts, which tends to be folks from academia, to help devise standards and like understand and like have the underlying methodology and data to point to, so that they can develop sort of like scientifically informed policies that are like sort of realistic and implementable. The companies are having a huge say in that, and so we need to like have like a balance to inform to policymakers. And then I think there is still like a huge role for AI research in academia, despite what may feel like. I want to remind everyone that today's fantastic generative AI was absolutely built from many, many, many ideas that emerged from decades old, as well as more recent academic and government-funded research projects. And like, this is not, I mean, I don't think the current paradigm is going to achieve AGI. So like, what is the next, what is the next paradigm? Where is that going to come from? It's going to come from blue sky research. And that's not what's currently happening in industry at the sort of time scale that they're thinking. So other things, so beyond just like AI research, we're thinking about how to advance AI capabilities beyond profit motives. Like I said, there's no such thing as a general purpose model. And what that means, when I talk to collaborators in other fields, is like they're really good at a lot of things, and they're also still really bad at a lot of things that they haven't been optimized to do. They just haven't seen the data. The data doesn't just exist on the internet. And so thinking about prioritizing use cases informed by, for example, the arts, humanities, disenfranchised communities, things that are not necessarily obviously possible. And that's like sort of not necessarily what many companies are going to do. thinking about not just sort of, again, user-centered, but human-centered understanding of AI impacts. So humans who are potentially using and being impacted by AI, who are not necessarily the users who are like paying for that product. And as I mentioned earlier, there's like so many crazy hard problems in like optimization and measurement, sort of life cycle assessment of AI models that incorporates, sort of from the beginning, from the hardware through end of life, and it's just like now you're incorporating a policy system, how to do attribution throughout that is interesting. There's a lot of math. Okay, so I'll wrap up there. Hopefully we have some time for questions. Thank you so much for coming and listening.
Thank you so much. Such a great talk. Any questions?
So I'm able to understand, like in the big pie of universal usage of energy, let's say we have usage of energy with industries, within households. So where does the usage of energy of like this AI infrastructure lies?
Yeah, that's a great number that I should know off the top of my head, but I don't. So yeah, in one of these slides, it was buried in there, but it's a really old number. So I think as of like 2022, it was like okay. This is not energy use. So this was total global greenhouse gas emissions. ICT, which is like computing generally, was like maybe 5%. So it's a subset of that. I think, again, at that time, estimated up to 30% of that. But it is rapidly growing. So yeah, what I should know is like, yeah, there are reports that have sort of number for like, I think data center is like a proxy to energy use. But I guess, yeah, we can look at those plots and kind of back it out. Yeah. So we're not, whatever this is sort of like the energy demand in all of Europe. Here, we're at 2025. So that's pretty significant. I mean, it's like, it depends on where you lie on this plot.
So that is CO2 consumption.
No, this is energy.
This is energy.
Yeah.
And what about like if we change the source of energy to renewable source? Like if the government mandates like all data centers should only use renewable source of energy, like would it still be a problem? Where do we?
Sorry, I had trouble thinking about things that are not possible, but yeah, that's not possible. But yeah, so I mean, so Vidya Gupta, who's like faculty at Cornell, has like a really cool, like nice line of work looking at this because he's much more focused on he's actually like a systems person, he's much more like hardware person, and he's much more focused on the embodied impacts. And so yeah, as we move to renewable energy, it's like right now the sort of operational energy is pretty important for ignoring those downstream impacts. But as we move towards renewable energy, the embodied impacts become much more significant and important. Yeah, he had a really nice statistic in this paper that sort of like basically to like equate the cost. So comparing like the embodied versus like sort of operational emissions, he was looking at like a Pixel whatever phone, and like the emissions to produce that phone. In order to equate that with like using the phone, you have to like run ImageNet classification constantly on the phone for like 3 years, which is like about like longer than the actual average lifetime of that phone, of the cell phone. So I guess that's fine. Yeah.
So it seems like a lot of the energy data is gotten from a lot of different resources at a lot of different time periods. So that makes the debate kind of very hard to, I guess, quantify or like actually have meaningful discussion on. How do you navigate these spaces?
I do a lot of like trying to get people to standardize reporting and get more data. I would say, like, I think we need more data. I think we're on track towards having more data. So yeah, one of the slides I skipped over is like even in the US, like in California, all companies operating in California, which means having users in California, which is like a lot of companies will have to have a like an environmental sustainability report that they release every year. The EU has like similar requirements, and there's like that does have a standard for like what needs to be reported and how. It's still a bit coarse-grained, but yeah. And then otherwise, I mean, I feel like I've been effective in just like trying to estimate things, and then sometimes the companies are like, "That was really wrong. Here's our actual data." I'm like, "Great, thank you." And then sometimes they're silent and they say other things like, "Nah, AI is just gonna like solve all the problems, though." And that's when you know, like, our estimates actually probably have other. But I don't know if that answers your question.
Thank you for your great talk. In this part, we focused a lot on the cost, the energy cost of the how we can like deploying such a battery on the training, making first time, probably not the models. Basically, is it possible that we can like calculate the gas energy cost because like that like besides the cost like the deployment and also like batteries.
Yes. Yeah, absolutely. And like that's something that I am thinking of when I talk about sort of like measurement and reporting standards. And also figuring out in this case sort of methodology. Like right now, yeah, there are a lot of statements, and then here and there, some sort of like case studies and examples, right, of like how AI has like had positive environmental impacts. But largely, like some statements that could be the case are made without the actual data backing it up. So when I talk about how, like in this discussion, like no one has the data to sort of back up their claims because we're not really thinking about this sort of like rebound effects, this like larger picture rather than just like sort of immediate energy use. That's exactly what I think, and I think we could do a much better job at that than we do currently. And yeah, I think it's possible, especially if you narrow down the scope to like, let's say, like electrification, like grid management or something, and kind of sort of explicitly say, this is all the energy that went into developing these models. We then actually deploy them in this grid. There's a subsidiary in Alphabet who's like working on this right now. And like here's like the
Yeah, well, thanks for the talk. Thanks for like breaking my mind a little bit with this downstream effects. I was not like thinking about that. And yeah, so I guess if you take like, yeah, if we just kind of AI will use as much energy as sort of we give it, kind of to speed up capitalism, use up more energy. I'm thinking of sort of, I hear your point on like the governance issues and kind of like creating those budget, sort of like how much we're going to give it. Of course, that's sort of depressing right now with the federal government, and also things like the Dave McCormick CMU Energy like summit with no mention of climate change, all this sort of stuff. So I'm thinking about other kind of friction points or your thoughts on this of like the cost of electricity, for example, being a finite thing, or can constrain these things, or like sort of the not in my backyard, don't build the data center here, here are the rules for the data centers, or I don't know if you have those kind of what we can do at this point, or
yeah, definitely. And the nice thing is that there actually is like a lot of data, like so data centers have been built in like Virginia for a long time now. We actually have really robust data on like the economic and localized impacts of so Northern Virginia is like the most centralized data center place maybe in the world. Definitely in the US, and most data centers are in the US. And yeah, and so they've had like tax incentives to build data centers there for like maybe a decade or more. And so that's nice. So that is and can be used to inform policy. So like when I mentioned, like it has been documented that ratepayers have seen increased rates, like basically because of data center energy. Sort of like use that data to help inform like what should rather than just having sort of tax incentives, we now can say, okay, maybe we want to give a tax incentive to build a data center here, but here's all of our constraints. It needs to have this level of efficiency, and we need to demonstrate, figuring out how to demonstrate that can't be impacting what people are paying. We need to be like testing, like not, let's say it's renewable, right? We need to look at like what the local air impacts are and things like this. So theoretically, it's doable. It's not what's happening. I was actually just chatting with someone involved in this stuff in Massachusetts, which is like the most democratic state. And Massachusetts just recently passed to a similar legislation, basically incentivizing building data centers in the state, with no caveats whatsoever of that kind. And I'm chatting with him. We're both like, what? Like, why? How? But yeah, we're not being informed, I guess. Trying to combat that would be good. Yeah. At the same time, there was, okay, so what company was it? Not Microsoft, maybe it was Microsoft. One of the tech companies, Amazon. Amazon wanted to, or I guess it's probably still working on this deal to purchase a bunch of energy from a different power plant that had been shut down in Susquehanna, actually, Pennsylvania. And actually, the initial agreement was denied, like it was not allowed through our like nuclear regulatory framework because they couldn't demonstrate that they wouldn't basically increase the cost burden on ratepayers. So I think that's a nice example of like in the US we do have regulations and they work sometimes to protect people, actually, especially when it comes to energy and nuclear energy.
That was like a federal regulation. All right, that's hard to say.
Yeah, I think. Yeah, that question might be outside of my like policy expertise,
sure.
But yeah, I think in the
That's
US, like
interesting.
nuclear
Yeah.
things, like tend to be like really
Sure.
federal.
Thanks.
I don't know if that's helpful, like a little
That's
positive
example.
note, I guess. Yes.
How much of the AI energy is focused on generative AI versus more specialized models? And is the utility from generative AI, or is it worth having that much more energy provided to it if it is the predominant source of energy increase?
That is like that's the question. It's such a good question. Yeah, if you can figure out and coordinate to like get like any sort of type of answer to that question that's like reasonably well-founded, like you will be doing very well. We don't have the data. So this is part of why, like, one of the things like I really want is like understanding like the sort of use cases. What are the models that are making up this energy use and our projected energy use? Because like I think we have no idea. These are similar to like inference being like a small amount of energy, but like a lot of times versus training being like more energy, fewer times. Similarly, like there are actually a lot of like embedded tiny little machine learning models everywhere, and like they're actually doing really effective things. When you think about like, buildings, making buildings more efficient, like it's not generative AI, obviously. It's like tiny embedded model with like 7 parameters per it. But it's potentially deployed more widely. So I think my hypothesized answer to this is like just I don't know if actually you want to say that. The thing I was going to say is like that the utility of generative AI is not equated by its current energy consumption, but then the issue is like how do we define utility? So you can like basically you could define utility in order to make an argument in any way you want. So like economic utility, whatever. Yeah, I'm not going to go into detail. There's a lot of it, like GDP, for example, like doesn't capture like a ton of like important aspects of the economy, like someone needs to care of children, they're not paying that person, they're not economy. So sorry, that was my rabbit hole, but I think it's a really interesting question that you can kind of career working on, and and options of that, right? And what are the next technologies? I don't know.
Thank you. I knew it was like a hard question.
Yeah, it's sort of a data thing. Even if we could get sort of like from data centers, let's say hyperscale data centers, where it's like one company sort of like controlling all of it, like what are the jobs that are running? What are they doing? Like that would be so interesting. What's that? Yeah. Sorry, yeah, sorry.
Thank you for the talk. One of the things I was sort of curious about was one of the main points that you had was that specialization is kind of one of those areas that we might be able to. And so I was sort of curious. I feel like the more you specialize, like let's say you just do a little bit of pre-training, post training, versus going and creating a whole model. The more you go down that kind of like rabbit hole, the more you have to deal with those first order effects of operational in the body, like training, holding all the data, and all this. So where do you think sort of along that spectrum we'll see value feels like maybe the wrong way to relate your internal use, but like where along that spectrum do you think you'll see like the most benefit, if that makes sense?
Yeah, so I think I might be over-interpreting the question into something I'm already thinking about, so I apologize, you can correct me. But I think it's like a really interesting question, and I think my students are actually working on a project that's like a small bite-sized piece of that right now. We're sort of looking at, let's say you have a fixed computation or like money, whatever, energy budget. So we could basically use that budget to like fine-tune and specialize a model to do a specific thing. Or we could use that budget, like we could not change the model, have a general purpose model, but use the budget to do like more inference, basically, right? And that's sort of like what generative AI looks like. General purpose model, but if you haven't trained it, like it might require like basically longer output, it will require longer outputs to do more reasoning. Or you can just like train it to like not have to do the reasoning in real time, right? It just like knows the thing. We don't have the results yet, but is that towards what you're thinking?
Yeah.
Yeah, and so in that sort of relatively small scope, yeah, they're sort of running that experiment across a bunch of different tasks to sort of try to figure out what those trade-offs look like. I mean, the high level thing is it's definitely really different depending on the task. Like some things actually sort of just require more real-time reasoning potentially, right, to do. Some things like classification, you just can kind of train it. Right? But yeah, I mean, I think that's like exactly like sort of my wheelhouse, or like what I like to think about it. Hopefully we'll have some interesting results. But the high level initial result that we do have is like, yeah, some tasks you don't like always want to specialize, some you sort of like never really want to specialize, and then I think there's like this sort of middle ground too, where you kind of like want to just encompass learning. Yeah. Or like where it's like a nod.
I guess, what insights would you have on discussing these issues with the general public?
Like from discussions with the general public, or
no, like I guess trying to explain the issues that come with trying to explain data energy usage to the general public.
Okay, I don't know if this is actually like answering your question. I have a lot of trouble sometimes, like people want like black and white answers, and like I don't think there are black and white answers, so I struggle sometimes with that. And like, how do we talk about this, but like in a way where people are gonna like take something away from it that's like concrete that we understand. That's kind of why like I don't really like just like converting stuff into like households and things like this. Like I don't. That's one thing, I guess. Like I struggle to figure out like how much depth do we need to like go into things in order to explain the nuanced stuff, or like how much should I just kind of like try to provide a black and white high level answer when it's maybe not entirely true, or like when I know it's not entirely true. Is that veering towards like answering your question, or like
Yeah.
Okay. Yeah, that's part of it, I guess. That's the biggest one, actually. And yeah, and this is general. I'm very frustrated. Like, I think there is this general situation right now that is very sort of black and white, two sides. You're either sort of like blindly pro AI, especially for the general public, not people who are educated on the details. Yeah, blindly pro AI to solve all of our problems. Like Sam Altman is our like board or whatever. And then there's folks who are like extremely anti-AI, like all data centers should be shut down. It is not good ever. And I think this is just like not like an effective, like with in many other issues right now, like I would like both, like neither way is right. Like neither side, neither of those perspectives I agree with. Like I do use AI and I do find it useful for things. At the same time, like, I want to be mindful, like, yeah, I want to be mindful that, like, yeah, we're not just like destroying the environment, we're doing like ethically bad things. But I think that there is, but I'm actually kind of optimistic, like, basically, I think that innovation and sustainability are not mutually exclusive. I think what I'm trying to tell you that is simple. So I think that like we can align AI development like with sustainability. It's just like we need to sort of try and like I don't know much better.
Maybe this kind of answered my question. I love your second to the last slide of role of universities. So what is like the role of AI researchers? I know you talked about like policymakers and stuff, but what is us as AI researchers? What are some of the things that we can do? Or what's the biggest thing?
Yeah, I mean, I'm saying this in a sort of idealistic, like I also have to apply for funding, so like I understand what the situation is like right now. But like we should be able to just like work on stuff that's like not immediately like competing with like tech companies or like getting the highest number on like the same benchmarks and stuff. We should be able to work on things that are kind of like just like interesting and cool. I think it's like not necessarily well aligned with like what the current funding landscape is right now, unfortunately. Although, yeah. And there's like so many different versions of that. So that's why I tried to come up with like some examples that are a little bit informed by things that I think about. I'm going to talk about in this talk of like, yeah, I think there's like a bajillion really, really interesting use cases where AI like fails all the time. I was talking to my friend the other day and I was like, you should really just be using Copilot. She builds like her business, like builds websites for people, like WordPress websites. And I'm like, you should definitely just like use Copilot to do all of this. And then she tried, she got back to me and she was like, actually like, didn't work at all in like very fundamental ways. And I'm like, yeah. And this is actually like a profit motive thing too, right? She's trying to make a profit. But like, I think the way that this is my hypothesis about what happened is like, yeah, AI is currently like awesome, like quite good at, in my opinion, at like a lot of like code generation and like coding stuff. But it's good at like, it's good at like the code that is on the internet, open source on GitHub. And actually like WordPress, like plugins is not represented there. And so it was just like making really dumb mistakes and just like referring to the wrong like API and stuff. It was like not up to date. And she was trying to put the API like in the. So I think that's like such a thing that you would say that is solved. Like her job basically should be like automated by AI, and it's not. And then so imagine in the arts and humanities, like there's so many interesting problems, and these models actually just like break down. And I think there's like interesting. It's not just applying. I think there's like really interesting fundamental questions about like how to adapt models under constrained budgets and things that would be really beneficial to a lot of people. And as well as, yeah, I'm really interested in sort of human factors stuff as well. I think there could be like way more interesting ways to collaborate with AI beyond like, the way that we currently do it. And that'll be much better, like much more effective and good for the economy if you like thinking about things in that way than like thinking about it as like trying to replace humans. It's like AI is good at stuff, humans are good at stuff. Like how do we have humans do the things that they're good at and we enjoy doing? Like the models do things that they're good at.
Thank you.
Okay, I feel like like, I don't know if we're way over, like, do not feel, like, if you need to leave or want to leave, you can leave. I can stay. I just want to make sure people aren't feeling, like, stressed, like, at being
Yeah, we have the room till 2, so
Okay.
more questions are welcome. But yeah, if you have something that you have to leave, feel free. But maybe before everyone leaves, let's give another round of applause. Thank you.
Okay, yeah, so.
How, some people are talking about like an AI bubble.
Yeah.
How do you expect that sort of to impact usage, energy usage in data centers?
Yeah, okay, so like, I'm not a finance person, so like, but I'll give you my opinions. Yeah. I like don't think, I have like other maybe concerns about like the current economic situation. But I'm actually like not that concerned about AI bubble. And this is for 2 reasons. One is that I don't think that, like, I'm sure they're overpromising. I don't think that they're overpromising that like insanely beyond like what AI actually can do. And that's based on my experience like a year ago, being like, this is hot garbage. Like, I actually like can use this for my work. And now I'm like, this is pretty useful, and I use it on a regular basis. And I can sort of see how, especially as we have more companies, figuring out how to do that specialization for like sort of various like useful economically whatever tasks, like it's gonna just work, like to put the engineering in, the data in, for a lot of things. That's one side. Other side that will close that gap to some extent, I think, is that even when it doesn't work, we are being that doesn't sound so terrible. Like, what I see happening now is like what I think happened, a decade or so ago with like social media. So I feel trapped where it's hard. I feel like I can't be like a social functioning member of society without having to interact with sort of social media and like Instagram. So like, even if I want to like support my like local businesses, like I sort of have to be on Instagram to find out like, what the bagel special is or whatever. And I think about this with my students a lot. Like I'm not on Twitter anymore, but in the earlier part of my career, Twitter was like extremely important for networking, for me to know and get the job that I did. And so I have my PhD students were like, I don't want to be a part of this, but like I have to. And so what happened there, is they sort of like lured us in and then added a lot more ads and kind of like made it worse. But now it's like a fundamental part of society that's like really hard to escape, or like you're potentially making really, really significant sacrifices if you choose to escape that. So I think we're seeing the exact same thing play out now with AI. So currently, it's largely provided for free, or like you can use AI a lot for free. And even when you're paying for it, you're paying way below cost. So AI providers, like OpenAI is not profit at all. Google's also not making profit off of their AI products right now. But it's to our benefit because we are becoming dependent on it. And we're going to have like many generation, like, yeah. And we're, especially sort of young people, I'm thinking about like coding and stuff, like, you're just like not going to learn certain things, like fundamental knowledge is going to be lost, actually, to the extent that we're going to have a workforce who lacks I think it's good to know how to use AI, but we're also going to have a lack of people who can function without AI in a lot of cases. So we're going to become dependent on the product, and then they can, like, OpenAI is adding ads now, right? And that's like, I'm so unhappy about just generally. Anyway, sorry. Think about this a lot as I use AI, and I'm like, wow, you want to run this product? It's really interesting. Yeah, and they're gonna just like, I don't know, they'll be able to increase the prices, but we're gonna be dependent on it, even when it doesn't. Because of legal laws. So sorry, that's a little depressing, but I actually think economically it will be fine. Like they will.
You said you worked with governments and different policymakers, sort of figuring out policy, measuring what they should do, of course. How are those sorts of collaborations come about?
Publish papers that they can use as like evidence or data to support policy stuff. And then they're like, who are these people? And they want to reach out to you. And then yeah, I think ultimately there's like not that, yeah. But I guess how do you know what that is? I don't know. Maybe I got lucky. But if you want, yeah, I mean, if you're interested, you can sort of think about just to start talking to, like, how do you, I don't know, you just start talking to policy people. Honestly, yeah, I think there are, if you're like sort of interested in that direction, there are like fellowships and stuff that, you know, bring you to DC and like can help initiate the networking, which is about knowing people, but I think like in order to like sort of do work that is interesting to people, like understanding how they're thinking about it and sort of what the problems are that they need answers to can be really helpful. And I think especially right now, people with computing expertise, AI expertise, like who are actually interested in being involved there, like they're interested in it. Yeah.
That's it. Thank you.
Thank you so much for staying. Thank you. Yeah, but do I need to be brought somewhere?
But I think.
Okay, perfect. I'm actually fine. Oh, you're not great.
No.
Cool. Yeah, thank you for asking. Yeah. I am gonna like probably be a little bit.
No.
Yeah, where do you wanna?
We can't meet you past 2 p.m.
I think that honestly, there's no one, there's no one.
Okay.
It's just like we officially booked the meeting room to, so we can't have.
I could get kicked out.
Yeah, my lab is
Yeah.
I just want to ask the meeting. So I didn't know some comments online, but I didn't like. I didn't. Okay.
I think
Should I come back like?
maybe you come back. Yeah, just like, I guess.
Yeah.
Yeah, exactly.
Such a bad.